Okay, so the next thing we're going to do is take a look at problems 5 and 6. So in problem 5, the information we're given before is that we've got this normally distributed variable of calorie consumption. It's got a mean of 3,700, a variance of 250,000, and we want to find the probability that it's greater than 3,000. Okay. So if we want a probability, first of all, it should be between 0 and 1. We should be able to rule out D right away. Okay. From there, what I had drawn ahead of time, my camera's giving me issues, is that I've got this normally distributed variable X. So I drew out that normal distribution. It's centered around the mean of 3,700, and I want the probability I see 3,000 or greater. So just like the uniform, the normal distribution is symmetric, so the mean should split it in half such that there's an area of 0.5 to the left of the mean, 0.5 to the right. So when I'm thinking about wanting to find the probability of being greater than 3,000, I know that that's going to be greater than 0.5. So I could go back and rule out anything above 0.5. Once again, this is a problem where I can rule everything out. I know the answer has to be A. But just in case I wasn't as nice on the exam and there was multiple possibly correct answers, the procedure from there is I need to turn that 3,000 into a Z value. Okay, so I've got the word here, but I'll kind of show you what lines up with on the formula sheet. So the formula sheet has kind of our just regular normally distributed variable X here. So I've got any normally distributed variable X, I can subtract the mean and divide by the standard deviation, and that would give me my Z value. Okay. Now here, we didn't have the standard deviation. All we had was the variance, but I know that the standard deviation is just the square root of the variance, so the square root of 250,000, and put it in my X value of 3,000, my mean of 3,700, and I get what, negative 1.4. So I then take that value of negative 1.4, or sorry, and I lied to you. I said we could rule out anything over 0.5. We knew that the area had to be, greater than 0.5. So I can rule out anything below 0.5. Sorry, I misspoke earlier. So when we're looking at this, I guess actually we can only rule out A. So it's going to either be B or C. Okay. So I'm going to look up that value of negative 1.4. Negative 1.40. So that first column, if we go up here, is 0.00. So negative 1.4 would be negative 1.40. The area to the left of that is 0.0808. Okay. So I just found that this area to the left, because the table always gives us the area to the left of our Z value, is 0.0808. I wanted the area to the right, which we said we know should be greater than 0.5. So I just subtract that 0.08 from 1. I get what? 0.9192. So if we go, excuse me, go back to that practice exam, 0.9192. Okay. The next question asks, excuse me, what's the probability we're in between 4,200, or no, sorry, what's the probability that we have more than 4,200 or less than 3,200? Okay. So this one, we're going to have a similar setup. Hopefully my camera doesn't do too much crazy autofocusing here. So we have the same sort of example. We've got a normally distributed variable. It's normally distributed around 3,700. I wanted the probability that I see it be below 3,200 or above 4,200. Okay. Now, one thing that's kind of nice if I notice, 3,200 is 500 away from the mean, and 4,200 is, sorry, not 5, is 500 away from the mean, and 4,200 is 500 away from the mean. So both these values are the same distance from the mean. Since this is a symmetric distribution, that means that it should fold on top of itself. And so these areas should be exactly the same. So as soon as I find one of them, I actually could just multiply that area by 2 or add it to itself, and I would have the other one as well. So I'll kind of work through that and show you. So what we're going to do is first turn that value of 3,200 into a Z value, find the area to the left. We could turn 4,200 into a Z value, find the area to the right. So we use that Z-score equation, which is just take the value you're interested in, subtract the mean, and divide by standard deviation, which was, we had the square root of 250,000. Now I could do this ahead of time. And I think if I find this is just 500, and then it becomes a little easier because I'm just plugging 500 in there. So if I do this, I end up finding this is a z-score of -1. Now, remember, the z-score tells us the number of standard deviations away from the mean we are. Well, if the standard deviation was 500 here, right, this denominator represented my standard deviation, then I'm 500 away from the mean. I should have a z-score of -1. I'm 500 below the mean. If I'm 500 above the mean, that should translate to a z-score of +1. Sure enough, if I plug in my value of 4,200 there, subtract the mean, divide by that standard deviation, I'll end up finding that that's a z-score of 1. Okay. So now, oops, I'll go to my table. I'll look up that z-value of -1, so -1.00, 0.1587. So let me just make sure that was clear. I went to that z-score of 1.00. That area to the left is 0.1587. So I just found this was 0.1587. Excuse me. I said it was symmetric, so I automatically knew this area was 0.1587. But let's just, in case I didn't have the exact same kind of number of standard deviations away on either side, what I could do is look up that z-value of +1 on my table. So if I do that, 1.00, the area to the left is 0.8413. So I think about here, the area to the left is 0.8413. I wanted the area to the right, so 1 minus 0.8413, which sure enough gets me that value of 0.1587. Now I wanted the probability to be in either one of these ranges, so 0.1587 plus 0.1587 gives me what, 0.3174. See if I can do math in my head correctly here. So if we go back to the answer key, to the practice exam, 0.3174 should be our answer there. Okay. Okay, so the next 3 questions kind of stem from that same initial information. We're just told that instead we have a sample of 25 people from this calorie consumption variable. What would kind of the distribution of those sample means be? Okay, so we want the mean and the standard deviation. If we look at the formula sheet, we'll kind of be reminded that when I'm looking at the sample mean, the variance is just the variance of the original variable I sampled from divided by my sample size. Okay. Now the mean of my sample means, let's see if I can get this to focus once I start drawing some stuff on here. Hopefully. If I draw more stuff on here, usually it'll focus in. And some contrasting colors so it focuses. Oh, come on. There we go. So I've got that originally distributed variable x. I'm thinking about the distribution of my sample means. So we said that as long as the original variable we sampled from was normally distributed, we actually didn't even need a sample size over 30. So if the original variable we sampled from is normally distributed, we know that our sample means will also be normally distributed. We also know that they'll be centered around whatever that true population mean is. So the mean of my sample means is just the original mean of whatever data I was sampling from, or whatever variable I was sampling from. So here I've got it centered around 3,700. I also know that the variance of my sample means is the variance of the original variable I was sampling from, so 250,000, divided by my sample size of 25. So we get a variance of 10,000. I believe the problem asked for the standard deviation. So we have one more step, which is just take the square root. So I get that standard deviation of 100. So if we're looking back here, mean is 3,700, and that variance, not the variance, the standard deviation should be 100. So this is one of the only problems where there could be some cascading errors. It's really important that you're able to determine what the mean of your sample means are, okay? And it's not hard, it's just whatever the mean of the original variable you sampled from was. So in problem 8, we're saying, okay, what's the probability that we see an average calorie consumption from the 25 people, or a sample mean from the 25 people, be less than 3,550? So we're thinking about what's the probability that I see a sample mean be less than 3,550. Okay. Well, if we go to the formula sheet, all right, go down here. Oh, there we go. Oh, I thought it was up here. Where's it at? There we go. Here it is. To turn a sample mean into a z-value, you take the sample mean and subtract the population mean, and then divide by what's in the denominator here is the standard deviation of our sample means. But we know we can calculate the standard deviation of our sample means from the previous problem, right, using this equation. Okay. So I'm going to take that value of 3,550, subtract the mean of my sample means, which is actually just the population mean. And then I'm going to divide by that standard deviation of my sample means. So I can go ahead and I can plug in that square root of 250,000 over my sample size of 25. Or if I was confident enough in my answer from the previous problem, I know that this should just be 100. I could just plug 100 in here, right? So it looks like I should have a z-value of -1.5. So the final step is we then go to that standard normal table. We look up -1.5. So -1.50 is that first column. So 0.0668. So this is 0.0668. And because we just wanted the probability being less than 3,550, we're done, right? So go back to the, I'm just moving things around. So 0.0668. Okay. Now, if I had asked you instead for something like the probability being greater than 3,550, we'd have one more step, which is subtract that 0.0668 from 1. Okay. Now, kind of answers we could have potentially ruled out here. Notice, once again, this is a symmetric distribution, so the area to the left and right of the mean is 0.5. So I know that my area is going to be less than 0.5. So I could have ruled out, I believe there's an answer on there that's like 0.9 something. Yeah, I could have ruled out 0.95 right away. Okay. Or sorry, 0.93 right away. In problem 9, if I want the probability that I'm greater than 3,500 but less than 3,700. Okay. So I'm looking at a kind of similar example. Let's hope we don't have the autofill. Now we're going to. So I've still got the distribution of my sample means here. It should be centered around that population mean of 3,700. See if we can get it to focus here. Stop moving. Oh, we'll see if I draw more of this out. Does that help? There we go. So I want the probability it's above 3,500 but below 3,700. So right away, once again, I know I can rule out anything above 0.5 because the area to the left of that mean, which is 3,700, is 0.5. So if I want something between 35 and 3,700, well, it's going to have to be less than 0.5. From here, I'm going to have to turn these two values into a z-score. Right. So this one should be easy. The z-score of the mean is always 0. And even if I try to plug that into my z-score formula for a sample mean, if I take 3,700, subtract 3,700, divide by the square root of 250,000 over 25, well, this is just always going to be a z-score of 0. And I know that the area to the left of that should be 0.5. I don't even have to look that one up in my table. Now this other value, I'll turn that into a z-score by taking the value of 3,500, subtract that mean of 3,700, divide by, remember this represented the standard deviation of my sample means. So I knew ahead of time this was actually just 100. So I think it was 100. Yeah, so I was going to have, this is going to end up being a z-score of -2, but I could plug everything in, just double check. Maybe I'm looking at this wrong, I'm doing the math correct in my head. But once I plug everything, sure enough, I get a z-score of -2. So I go to the table, I look up a z-score of -2.00, so 0.0228. So this would be 0.0228. Remember, I wanted the probability of being in between these two values. So I'll take the smaller area and subtract it from the larger area. So 0.5 minus 0.0228, and it should give us, go back to the problems here. So that'd be what, 0.4772. Now this is another, we said it had to be less than 0.5, so we could have ruled out C right away.